So let's begin with the second part of atomic structure. So let's just recap what we studied in the last class. So we studied about discovery of fundamental particles. What are the fundamental particles? Electron, proton and neutron. So the particles, let's write down the particles, their symbols, mass and charge. So we studied all this in the last class. So the particle electron was discovered with cathode rays. Proton was discovered with anode rays. Both use the same apparatus. Neutron was discovered when alpha particles were bombarded on beryllium, and the product were carbon and one something which had mass but did not have charge. So thus the neutron was discovered. Symbol of the electron is -1 E0. -1 is the charge, this is the symbol, and this is the mass. So mass is, we have written 0 because it is negligible compared to the proton and neutron. Actual mass of the electron is 9.1 × 10⁻³ kg and its charge is 1.6 × 10⁻19 coulomb. Coulomb is the SI unit of charge. For proton, symbol is H11. So the nucleus of the hydrogen atom itself is a proton. So we write the proton as 1H1. Mass of the proton 1.67 × 10⁻27 kg. Mass of neutron is also similar to mass of proton. It's a bit more than proton, but for our sake let's take it as same. Again, the charge on the proton 1.6 × 10⁻19 coulomb and neutron is neutral. So above 3 are the fundamental particles present in all atoms except hydrogen, because hydrogen does not have neutron. So before we move forward about the atomic structure, since we will be dealing a lot with the electrons and protons, let's talk about the properties of charge. So these properties are they can be applied to any charge, not just proton and neutron. So they are very fundamental properties. You must be knowing most of them already. So first, they are of two types, positive and negative. Example is if hydrogen atom breaks into the ion H+ and electron E-, the E- will have negative charge and H+ will have positive charge. This charge E is denoted by it can be either on an electron or hydrogen ion, but it is denoted by symbol E, whose value is 1.6 × 10⁻19 coulomb. E here does not mean electron, it just means charge on an electron, magnitude of the charge on an electron. So it is the most fundamental charge. There is no charge which is less than the electron, that's why it's denoted with a symbol E. So E means 1.6 × 10⁻19 coulomb. So electron will naturally have -E charge and proton will have +E charge. So don't think that since this is plus and this is minus, this charge is more than that. It's just that their natures are different. So we randomly took one as negative, so other became positive. So this does not mean that the proton has higher charge. Both E and P have same charge, but their nature is different. Second, charge is quantized. What quantized means is, for example, when you are playing football, or you either play with 11 players, or you play with 9 players, or you play with 2 players on one side of the team. You don't play with 2.5 players. So in football, the number of the players can only be the integer value. Similarly, in charge also, all the charges have only integer values of E. So charge on, for example, Mg + 2 will be +2E. Na + 1/2 is not possible. So we can write Q is equal to Ne, where N is an integer. So we are not just talking about the charge on the ions. This can be any charge. All the charge anywhere, it has to be an integral multiple of E. Third, like charges repel and opposite charges attract. This also you would have read in your earlier classes. So plus and plus will repel each other, minus and minus will repel each other, but plus and minus will attract each other. And this force will naturally be along the line joining the two charges. So it cannot be that the force can be in this direction. This is not possible. So charge has to be in the direction of the line joining the two. So the force between the two charges has to be along the line joining the two charges. Fourth, magnitude of that force which we are talking about between two charges placed at a distance r is given by F is equal to 1 by 4 pi epsilon q1 q2 by r square. This can also be written as k q1 q2 by r square, where k is 1 upon 4 pi epsilon and its value is 9 into 10 to the power 9. Before moving forward, let's discuss a bit of a mathematics here concerning the conversion of units. So it is important because in charges we normally deal with very less quantity of charge. For example, a charge on a electron is 1.6 into 10 to the power minus 19 coulomb. So we will need some unit conversions in order to study the atomic structure properly. Even the distances at the atomic level are very less. So we will need to get this part very clear before we move forward. How do we convert one unit to another? So one simple example is if you want to convert 40 kg into grams. So this is very simple. So you can directly say that it will be 40,000 grams. But let's do it in a systematic way. So here we introduce the concept of conversion factor. So we simply write 1 kg is equal to 1000 grams. We take 1 kg at the denominator of this side of the equation. So this becomes 1 is equal to 1000 gram by kg. So when we say 1 on the left hand side, it does not have any unit. So we can multiply this quantity to anything and still the value of that quantity will not change because it is as simple as multiplying that quantity by 1. So this thing which we get on the right hand side is called the conversion factor. So this conversion factor we will use whenever we are talking about the changing in units. So in this example 40 kg, so we can multiply 40 kg by 1. So here in this case it is 1000 gram by kg. Kg cancelled, so it becomes 40,000 gram. So this is a simple example, but we'll do some difficult conversion of unit problems also, where we will use the same concept. We will write it simply between the two units. We'll take one on the one side and we'll take the rest of the things on the other side. So this thing which you will get, which is a conversion factor, we'll simply multiply this conversion factor to the quantity which we want to convert, and then we'll see that the denominator cancels out and we'll get our whatever we want as the in the denominator as the new unit. So it's important to note that only the units are changed. The quantity and the value is same. For example, 20 elephants, I can write 2 into 0.2 centi elements, but still it is 20 elephants. So the number of elephants is not changing, only the unit is changing. So since in the atomic structure we talk about the distances which are very less, so we need to introduce some distance units. So let's start with the Armstrong. Armstrong is 10 raised to the power minus 10 meter. Second is nanometer, which is 10 raised to the power minus 9 meter. Then there is micrometer, which is 10 raised to the power minus 6 meters. So if you just focus on this, you can see that if you multiply Armstrong by 10, you get nanometer. So you can directly say that 10 Armstrong is 1 nanometer. Simply, if you see here, if you multiply 10 to the power minus 9 by 10 to the power by 1000, you get 10 to the power minus 6 meter, which also means that 1000 nanometer is same as 1 micrometer. So let's do one example, a few examples to convert 10 Armstrong into nanometer. So again we'll do this problem with the conversion factor which we just learned. So 1 Armstrong times 10 is 1 nanometer. As you can see from here, if you multiply this by 10, it becomes 1 nanometer. So we'll take this on the bottom. So 1 is equal to 1 nanometer upon 10 Armstrong. So here we get 10 Armstrong, which is what we have been asked to find out, which we are asked to convert into nanometer. is equal to 10 Armstrong into, this is the conversion factor which we can multiply. The Armstrong cancel, it becomes 1 nanometer. Second and third you can try in your notebook before seeing the solution. So 300 nanometer into Armstrong. So again, we are from this equation, if we, instead of taking this on the right side, if we take 1 nanometer on the bottom, this becomes 1 is equal to 10 Armstrong upon nanometer. Now we multiply this into 300 nanometer. So conversion factor is just the reverse of this. So as it is 1 by 1 is also 1. So you can reverse this and multiply to any quantity. It doesn't change anything. So 300 nanometer into 10 Armstrong upon nm. So nanometer cancel. This becomes 3000 Armstrong. Now finally, to convert meter into some 5 into 10 to the power minus 7 meter into Armstrong. So again, let's write 1 Armstrong. This we directly know is equal to 10 to the power minus 10 meter. So we take again this on the bottom. So you remember, whatever we want to remove, we keep it at the bottom, and whatever we want, we keep it at the top. So in this case, what we want, nanometer. So in the conversion factor, we'll keep nanometer on the top. What we want to remove, Armstrong. So we'll keep Armstrong at the bottom. In second example, we want to remove nanometer. So we'll keep nanometer at the bottom. And we want to have Armstrong. So we'll keep Armstrong on the top. So that way, when we multiply this by this quantity, nanometer and nanometer will get cancelled out. So for this third example, we want to convert meter into Armstrong. So what we want at the bottom, meter. What we want on the top, Armstrong. So now when we write 1 Armstrong is equal to 10 to the power minus 10 meter, we clearly need to take this down. So that way we get Armstrong on the top and meter at the bottom. So 1 is equal to Armstrong upon 10 to the power minus 10 meter. So this conversion factor again will multiply to 5 into 10 to the power minus 10 meter minus 7 meter. And again, meter and meter will get cancelled out. Sorry, meter and this meter will get cancelled out, and we'll get 5 into 10 to the power minus 7 upon 10 to the power minus 10 Armstrong. Actually, I should have written meter here. Yeah. So this meter and this meter will cancel out, and this will become 5000 Armstrong. Now we'll learn about certain terms. So it will be these might be very confusing terms, so it's better to get a clear understanding on what they are now itself. So the potential and potential energy. So we need to understand what is potential energy, and what is the relation between them. So in one line it will be very clear. So let's read that. If a charge Q is placed at a surface having potential V volt, then potential energy E of that charge is given by E is equal to Q into V. So when we say V in volts, that is SI unit, Q has to be in coulombs, and then you will get E energy in joules. So this is the equation which relates potential, charge and potential energy. Now next term is electron volt. So electron volt is a unit of energy. It's energy of an electron at 1 volt. So if you put Q as the electronic charge, and you put V as 1 volt, whatever you get here, that is 1 electron volt. So let's do that. So let's put Q as 1.6 into 10 to the minus 19 and V is 1. So this becomes, both are in SI units. Q 1.6 into 10 to the minus 19 coulomb. Coulomb is in SI and voltage is also in SI. So we get the answer in SI units, 1.6 into 10 to the power minus 19 joule. That is the 1 electron volt. So 1 electron volt is the unit of energy, where Q is equal to E and V is equal to 1 volt. Let us clear one more concept which you would have learned in your earlier classes about the mole. So 1 mole is 6.023 into 10 to the power 23. That's it. It does not have any unit. So mole is actually a quantity, number. So it's not like 1 kg is equal to 1000 grams. It's not like that. 1 mole is a number. It's unitless. 6.023 into 10 to the power 23. So we'll study about mole later in depth in the chapter of mole concept. But for now, let's do one simple, again some questions on conversion. Convert 1 electron volt into kilojoule per mole. This is a little bit difficult, but just try it in your notebook before looking at the solution. So let's solve this. So we know that 1 electron volt is 1.6 into 10 to the power minus 19 joule, as we just did in the last slide. So now let's introduce our conversion factor back into picture. Till now we were multiplying this by just one conversion factor, but since we can multiply by 1 as many times as we want, we can multiply it by as many conversion factors as we want. So let's look at the first conversion factor. So 1 mole is equal to 6.023 into 10 to the power 23. So if we bring the mole down, it becomes 1 is equal to 6.023 10 to the power 23 upon mole. So basically whatever we want to get here, get the conversion factor in that sense. So we can see that mole is at the denominator, so we'll get mole at the denominator. Now we need kilo at the numerator, so let's do that. So we can say 1000 is equal to kilo. Again, this is also a quantity, unit of quantity. So it's not unit of quantity, k represents quantity, so it's unitless. So 1 is equal to k by 1000. So since we need k on the top, we got the conversion factor with k on the top. So now we will multiply both these conversion factors to what we originally have, which is 1 electron volt. So 1 electron volt is equal to 1.6 into 10 to the minus 19 joule times first conversion factor times second conversion factor. So joule into k becomes kilojoule and mole will be mole. So this will come out to be 96 kilojoule per mole. You can remember this, 1 electron volt is equal to 96 into 96 kilojoule per mole. Even if you don't remember, it's okay, but if you can, it will be good. So let's do this problem. A charge 5e. See, it is 5e. It cannot be 5.5e. It cannot be 5.75e because charge is quantized. So charge 5e is placed in an electric field of potential 20 volt. Calculates its potential energy in units of eV, joule and kilojoule per mole. Now we know the formula, E is equal to QE. So let's first get the normal, let's get it normally. So we replace Q by 5E and V by 20 volt. We get it 100 EV. So we directly get the answer in form of EV because we are not writing the E as 1.6 into 10 to the power minus 19 coulomb. So when we are asked to find it in terms of EV, you don't need to change the E into its charge in coulombs. You can directly write it as just E. For second part, since now SI units are concerned, we need to write E in its SI unit. So E is 1.6 into 10 to the power minus 19 joule. So joule is in SI and V is in SI. So both C coulomb and V are in SI. So this becomes 1.6 into 10 to the power minus 17 joules. Third, kilojoule per mole. So we just did in the last question the conversion factor, how to use the conversion factor to convert it into kilojoule per mole. So we already have the answer in joules. So let's convert it into kilojoule per mole. So this becomes K by 1000 into the first conversion factor into second conversion factor. This comes out to be 9.6 into 9.6 kilojoule per mole. So if you remember in the last question, let me just from the last question, you can either I'm not sure it is recorded or not. Okay, but I'll explain it again in that case if it's not recorded. So from the last question, it was 1 EV is equal to 96 kilojoule per mole. So what we can do is from here directly we can instead of EV we can write 96 kilojoule per mole. So this becomes 9.6 into 10 to the power 3 kilojoule per mole. So you can directly get it from here if you remember that 1 eV is equal to 96 kilojoule per. Let's do a few more questions where you won't be asked to find E but some other quantity like Q and V instead of the E. So if E is given, and Q is not given, you can find V, or if E is given and V is given, then you can find Q. So in first question you are given the energy in EV, you are given V, and you are supposed to find Q. So just replace them, 200 EV. So it's important to write units here. So this is not in SI units. So but you still write just EV because you need to just find Q. So Q will come in terms of E. That is fine. Is equal to Q times 20 volts. So just VV cancel. This 20 goes down. So Q becomes 10 E. So it's fine if you leave the answer like that instead of converting E into 1.6 into 10 to the power minus 19 coulomb. So in this question again, E is given, Q is not given. You are supposed to find V. So let's write the V as V naught to avoid confusion with the units. So E we can write 1.6 EV, Q will be 2E, and V naught we are supposed to find. So this goes down, E and E cancel, this becomes 0.8 volt. So now that the basic mathematics is out of the way, we can get back to our atomic models. So in the logical flow, what we studied till now is the particles were discovered. So once the particles are discovered, naturally we start to think that how they are arranged inside an atom. We know that the atom has these particles, but how they are arranged. So this is how the atomic models theory started. So we will study these two, Thomson's model and Rutherford's model, as both of them are the important ones. So Thomson's model is pretty much straightforward. It's also called as plum pudding model. So he just proposed that the atom consists of a positively charged uniform sphere where electrons are embedded inside. It's like a watermelon with the seeds inside. So watermelon will be the positive charged uniform sphere, and the seeds inside that watermelon will be the electrons. So this theory proved wrong, as later in the experiments done by the Rutherford, so it could not explain a certain things which were in those experiments. So after the experiment by the Rutherford, he proposed his own model which was close to what the actual model was, but this Thomson's model was clearly disproved by the Rutherford's famous gold foil experiment. So let us study that now. So Rutherford's famous gold foil experiment. Famous is let's just say whenever you mention, you might say that it's famous. So let's discuss the apparatus first. So this is a lead box in which a radioactive particle is kept here which emits alpha particles. So there will be a slit here which will focus these alpha particles on a gold plate. So at the back of this gold plate there will be a screen. This will be covered with ZNS coating, the same ZNS coating which we put on our cathode tubes. So whenever those alpha particles will hit this ZNS coating, there will be some glow, which were studied by the Rutherford. So we have a lead box where the alpha particle source is kept, and these alpha particles are bombarded on a gold foil. And on the fluorescent ZNS screen, it is noted that where the flash is produced by these scattered alpha particles are put. So it was observed that most of the alpha particles went straight through the gold foil, and most of the flashes were observed at this part. Few alpha particles scattered and deflected, and therefore the flashes were observed at some distances away from the center as well. A very few, the least number, In fact, they were 1 in 20,000. So 1 in 20,000 took actual U-turn. So they deflected by an angle of 180 degree. So let's note down the observations from his gold foil experiment. So it's just that 99% passed through, few deflected at small angles, this and this, and 1 in 20,000, like very few, came back at almost 180 degree deflection. So now we will discuss about what conclusions Rutherford drew from all these observations. So conclusions and therefore nuclear model of atom. So in this slide we will discuss about the conclusions, and next slide we will discuss about the model which Rutherford proposed based on his conclusions. So first, mostly atom is hollow. Since most of the particles, alpha particles, are going straight through, then most of the atom is hollow. Makes sense? Second, it has concentrated positive charge. So since a few alpha particles are getting deflected, alpha particles are positively charged. What are the alpha particles? They are the helium nucleus. So some of them are deflected, so they are positively charged, so there must be concentrated positive charge which is making these alpha particles deflected. Finally, there is something very heavy, because when some of the alpha particle itself is heavy, and when some of the alpha particles are taking a U-turn, deflecting by 180 degree, that means they are hitting something which is very heavy. Only then they will be turning back and deflecting at large angles. So he drew these conclusions, and based on these conclusions he proposed his nuclear model. So this concentrated positive charge he called as nucleus, and that was the basis of his nuclear model. Okay, so this is the homework for you. For the conversion factor in your book Nutan Chemistry, on the page 14 you can read about the theory. Deep reading, that means you need to concentrate what's written there. And on the page 15 there are these 4-5 examples that you can do, and you can do a general revision for the last class and this. So from page 93 to 100, so you can generally go through the pages. You need not like focus too much, you need not understand everything, just go through it and do a light reading. But this is the important part, because this is the basis of mathematics. It's not just important here, it will be useful in your physics and maths as well. So that's the end of this lecture. Call me when it's done.